any polygon can be broken up into triangles, right? So there are different manipulations of how we can deal with the base that is not a triangle or a square. But from here, we could take the 96, multiply it by 3 actually, then divide, or solve it in a couple different ways. We could get a height of 9.6, but that's not really necessary, right? Because they tell us we have the same base area and height. Well, what relationship do we find between cones and pyramids? When talking, okay, they both go to a point. That's an interesting one. I don't know that that matters right here, but that's an interesting one. They say it has the same base area, so that circle's area is 30. The height is also 9.6. We figured that out. We don't really care, but we figured that out. What's the volume then of this cone? Also 96. Because an application of Cavalier's principle is that if we have the same base area and the same height, that really a pyramid is a cone, is a pyramid is a cone, like kind of back and forth, if we're talking about volume. Now, where does surface area get tricky when it comes to cones? What does the surface area of a cone make? If you look at the net of a cone. Did we talk about this stuff in Math 1? Because this is where I can't remember. It's a Math 2 standard, so I have to make sure that you know how to do it, because we like teach to the standards. If you take apart a cone, the bottom of it is going to be a circle, right? But the top part of it, instead of being triangles, I mean, they're kind of like triangles. Close. Let me see if, I don't know if my 3D shapes got lost or if they made it over here. A lot of my things did not make it to my classroom. It smells like new inside that cabinet. I don't know if you guys know what I mean by like when something smells like new. Alright. So, we've got some examples here. And for our pyramid that has a same diameter, right, same distance across, but not actually same area then, we know that our net is triangles, and we could actually put these together and just make a big trapezoid if we wanted, depending on the size of the base. You could either make a trapezoid or a parallelogram with the triangles. Hey guys, I'm trying to get you curious about something forward so then we can come backwards. This part of the net is actually, so ignore this, what is this shape actually? It's part of a circle. The thing that's going to determine how much of a circle, whether it's a little less than half or a little more than half, or are the dimensions of the pyramid, right? The height of the pyramid related to the circumference of the base, right? So if we think about how big will these, and actually if you look at this side, it's almost a little bit easier to see, they're like little pizza slices, right? Because if you imagine the bottom of it has to be rounded, the actual, unless these were all, this might be easier to see if my dot camera might actually show like the light well. If these were flat, they would all be like pizza slices, but they're not in reality. Right, this is having a hard time because there's nothing for it to focus on. There we go. So in reality, these aren't flat edges right here, right? This is a curve. And in reality, this isn't flat when we look at it. It is right now, like literally what I'm holding is a flat object, but it's actually curved, right? It's a little bit like conical, it's rounded. So when we flatten it out, each of these is a pizza slice. But man, to figure out how much of the circle we have, we need to know what is this amount. Well, what is this edge of the shape going to come from? The circumference of the base. What is this distance going to come from? Close. Think about it. Think about when we put this up. I mean, it is the radius of the resulting partial circle. Yes, you're not wrong. But what it is when we look at the 3D shape, it's not the height. This is where this gets really tricky. So what we are looking at there is actually this, the slant height, right? So this is what we call our height, and this is what we call our slant height. So please look on your formula sheet down at the bottom right. We then call that S, but it's actually like the hypotenuse of the triangle formed with the radius of the base and the height of the cone. Take a moment to let that get in your brain. Does that statement make sense? That it's going to be the hypotenuse of the right triangle formed by the radius of the cone and the slant height, and the height of the cone is how we get to our slant height. So all of this to say, let's come back up here and try to derive some simpler formulas. So they've got a formula for cube and a cuboid, which is a rectangular prism. Ignore the pyramids for a moment. I want to look just at prisms. And I probably should have cut this and put it up. I probably should have put these in a different order, but this is actually the order they're normally presented in. Just to throw some formulas at you really quickly. In general, though, so this part that I left open in the middle. In general, how can we talk about the volume of a prism? We've been doing this since Math 8. We use a big something. Yeah, but there's an even easier way to say that. Yeah, big B times H really is one easy way that we can remember. Big B is always the base area. So that's not very tricky to see, but the next one. Prism and cylinder surface area. So if we look at all the surface area formulas, we've got 2 of the front faces, 2 of the side faces, 2 of the top and bottom faces. I probably said those in the wrong order. 6 of the same size faces. Coming down here, I've got some rectangles around the sides, and then I've got matching bases. What's one characteristic that always has to be true in a prism or a cylinder? Prisms and cylinders always have 2 of what? prisms and cylinders always have what in common? Two matching bases, right? Two identical or two congruent, we could say, bases. So there will always be 2 times big B. If we're trying to simplify the formulas that we're writing a little bit, there will always be 2 times big B. But if I start looking at the shape without the bases, what's left over in a prism or a cylinder? Guys, I think this is a review from Math 8, so if you're being quiet because you're like, we already know this, just go ahead and speak up. But if we forget it at some of the time, what shape do we actually have in any of these if we get rid of the bases? I'm going to grab the most complicated one that I have. Yeah, a rectangle, right? If I remove my bases, if I get rid of these hexagons, which we can turn into triangles, we can deal with them in a minute. If I remove those, all we have is a rectangle. How would we figure out the entire area of that rectangle at once, instead of having to break up all that nonsense like they did? Yeah, the height times the total base edge. So whether you want to say perimeter of the base or how you want to write that, I don't care what notation you actually use to write that, but it's going to be, we have 2 bases and the height times the perimeter of the base. So what you could say is P sub base. We can start to use subscript notation, guys, and we could also just write it like this to clean this up a little bit. And guys, that works for cylinders too, which is what most kids struggle to understand, is that even though this edge is a curve, like your spaghetti noodle that is a curve, can we lay it out straight? Yes. It started straight, then we put it in boiling water. It wasn't straight anymore. We could lay it back out straight. So if I straighten this back out, it's still a rectangle. This perimeter of the base, in this case, is circumference, but we know circumference is perimeter of a circle. All because it's circumference doesn't mean it's not perimeter. So I know I'm probably over teaching this because I also teach this to my Math 8 kids. And that's where they are making the mistakes of not realizing that we can just turn that into a rectangle. I think you guys are probably ready for me to move on. So we'll come back to talk about are there any other shortcuts? Actually, do you guys see, before we move on, do you see any other shortcut notations for maybe if we're doing pyramids relating? Yeah, so for pyramid volume, it's the same as this, but then just 1/3. So if you want to say that, for a pyramid, it's really just 1/3. So you can make a little notation if you wanted. I can't draw a pyramid. But yeah, that's pretty simple. What about surface area? And this, guys, sometimes there isn't. Man, surface area of a pyramid. It's so we're always still going to have the base. So we always do have base area. When we start looking at these faces, these faces around the... By the way, guys, this is the vocabulary that I'm going to expect that we start to use. If you say point, I'm going to say decimal. This is not a point, it's a vertex, right? Or a vertex, if we're talking about multiples of them. This is not a side. Side is what comes with your hamburger. There are edges and faces. right? So I know this starts to get annoying, but trust me, it will help you in the long run to stop using the words that have too many meanings. Point has too many meanings. Side has too many meanings. Edge, face, vertice. So our faces around here. Okay, this is an easy question, but what shape are these faces for a pyramid? Triangles. So triangles we know are 1/2. Yeah, half of a square, so half of like the base times the height is the normal formula. Crap. There's a really complicated formula over here on the regular tetrahedron. What's a regular tetrahedron? This is not a regular tetrahedron. Sorry, what is it, Ellie? Or I don't care. Yeah, every face is identical. So if I flip this sideways, you can tell it's sideways. That's what makes this not a regular tetrahedron. If this bottom face was the same as my other faces, then it would be a regular tetrahedron. So regular literally means all your edges are the same. So every edge is B. Whereas any other pyramid that is not a tetrahedron has faces that are different. And so this is a triangular base pyramid that is not a tetrahedron, right? If it is, it just has that more particularness. We've got rectangular based pyramids, right? This is square, but we could also have rectangular based. Guys, if I'm trying to find the face area, do I use this edge? We have to use this. If you can draw, I don't know if you can visualize this, but if you can draw here on the left, or more so kind of front, I visualize this as left and I visualize this as front, in a way, the one that I drew my lines on. We have to use the S and the slant height. Just like in our cone, we had a slant height. Now that's why I don't like using S over here. So I'm going to tell you, if you want to change the notation here, we use S down by our cone for slant height, but up here they're using S for the side of the base. I disagree. First off, I disagree with them using side, but they're using it because it's a square. So little s normally means the edge of a square. That's why they're using little s, but I disagree with that. So if you want to use something else, I normally use little b for a base edge. So if you want to use little b here, but be careful, when we go to solve these problems, you don't use the height and you don't use the edge of the pyramid. We have to use the slanted height. Any questions? I know I'm kind of driving into this a bit much. When we're doing volume comparisons, just to make sure that we cover all this stuff before we move on, because I should have already talked about this before we dove into the formula sheet. What do we look for is ratios between base areas, because that's what is going to tell us if they are the same. Right, ratios between heights, because again, if our base areas and our heights are the same, then our volumes are going to be the same. And are they both similar shapes, right? So a pyramid and a cone are similar shapes, but a pyramid and a prism share that ratio, right? So in situations like this, where they tell us we have a height of 2 units, volume of 18 cubic units, the oblique rectangular prism has a congruent base and the same height and its slant height of 3 units, what are we going to do here? Sorry, did you say divide or multiply? That's why I gave you the chance to just say, like, oh yeah, it was my mask. I said multiply. If we have the volume of the pyramid, right, 18 cubic units, the volume of the prism compared to that pyramid, if it's got the same base area, check. If it's got the same height, check. The relationship between prism and pyramid is times 3 or 1/3. right? So here, we would multiply the pyramid by 3 to get the prism. Make sense? Calvin, what about here? This is, I don't know if you've done this homework yet. This one's a little tricky. It's okay if you don't know how to solve this. It took me a minute to remember exactly what to do. That's a good guess. That was my guess. Guess what? I was wrong. I'm serious. That was when I first looked at this, when I was trying to remember. Because, guys, even though math teachers teach math, we don't always remember everything right off the bat. So they said compare base areas and compare heights. Let's go with the easy one first. Are the heights the same? Good, check. Are the base areas the same? No, we don't even know the areas. Balls. It's an equilateral triangle. Yay. We could do some complicated math and some trigonometry and derive base areas. Or we'd use ratios. How does a square... Let's go square because life is easy when we use squares. How does a square of 2 by 2 relate to a square of 6 by 6 when we're talking about area? Multiply by 3. So my area of 4 here becomes an area of 12 here. What should we multiply by here? Not 1.5, because not 3. What is the area of my 6 by 6? 36. How do we get from 4 to 36? Ooh, 9. This. Oh, we're not looking at lengths. We are looking at areas. And areas share squared relationships, not direct ratios, but literally that ratio squared. So what we're going to do in this situation is, I agree with you. To get from 4 to 6, that's times 3 halves. But to get the new area, B is going to be 3 halves squared times A. You might want to jot a quick note of that in case you're going to forget before you go to do that homework. Anytime they give you length comparisons, we take the ratio of lengths and square it. So, and this is on your homework. There are not very many of these problems, so the chances of you getting this problem are kind of high. So what I'm really saying is the volume of B will be 9/4 the volume of A. Because the lengths had that ratio of 3 halves, we took that and squared it. Questions on why we do that? Areas always have a square relationship. Whatever happens to the length, that squared happens to the area. Guys, whether we're working with circles, triangles, hexagons, that relationship always happens. Whatever happens to the length, the area is that ratio squared. I sometimes forget that doesn't erase like a smart board. So here, the last kind of like trap door that I wanted to warn you guys about and make sure that you don't fall into. Well, I try to make sure I don't fall into not knowing what the schedule is today. You're in here for 15 more minutes. Yes. Today's the 10th, right? Yeah. Does the slant height here matter? Take a moment. Does the slant height here matter? Because we talked about a couple situations where slant height does matter. What do you need to know to be able to determine, does the slant height matter? Okay, height of 5 units on pyramid B has the same base area and height. Okay, so we know same base area, we know same height. What are we being asked for here? We don't know. To answer the question, does the slant height matter? Well, does the slant height matter if we're deriving volume? No. This is a distractor. Used in this situation, the slant height is a distractor. However, does the slant height matter if we're deriving area? Yeah. So, what this leads us to is a mathematical principle about optimization. Optimization is when, in mathematics, we say, I need to satisfy X, Y, Z. I want to minimize A, B, C. So maybe your favorite cereal, Reese Puffs, decides we need to use less cardboard in our boxes. Is there any way to redesign our box with the same volume but use less cardboard? That's an optimization problem. Most prisms are a little fixed, right? Like, there's only so much you can do with squares, but triangular objects or rounded objects start to become really interesting. Which ice cream cone does the store buy? Well, how much ice cream do you want to fit in the cone, right? How much ice cream do you want to have to give on each cone? Does it matter if I go from a round cylindrical type ice cream cone to a round pyramid, a round like cone type ice cream cone? And if you guys aren't visualizing what I'm seeing, this doesn't make sense. But you know, there's like McDonald's are like cylinder ice cream cones. And then like if I go to like a real mom and pop ice cream store, normally they're like waffle cones, right? So like these are the sort of things where we're going to use solid geometry out in the real world. So let's talk about how we apply this. What is the volume of our oblique prism, oblique triangular pyramid? What is this, the fourth time? Oblique triangular prism there. So we said for prisms, we just need base area and height. Are we able to derive the base area here? Yeah, because it's a right triangle. Go ahead and try this on your own. Let's make sure we get the same answers. Cavalieri's principle says it doesn't matter that this is oblique, right? Oh, are both of you guys already done? What's our volume here? 66. So how do we get that? How'd you get 6? Half 12? Boom, boom, boom. All right, so volume sounds easy. Get your surface area. This is where I push you beyond what Khan says, and I didn't type it up there, but calculate your surface area here. Yeah, now you're like, oh, man. Do we have to do the Pythagorean theorem more than once? Actually, do we even have to do the Pythagorean theorem? No, everything's given to us, right? So, guys, if this is 12, what will these two be? Also 12, right? I know that sometimes it sounds like we're like a little slow in the brain as math teachers ask easy questions. But that's what I wanted to make sure that you see is this is 12, right? Like this edge is 12, this edge is 12. So all of these rectangles, even if they're tilted oblique, Cavalier's principle says that don't matter. As long as everything was pulled together. Remember, Cavalier's principle works in 2 dimensions and in 3 dimensions. So even for that 2-dimensional shape, it's rectangular, right? So 3 by 12, 4 by 12, 5 by 12 on the back. Cool. We don't actually have to like add it all together. I just want to make sure that we would know how to solve it. Oh, is that everything I planned for today? That was everything I planned for today, apparently. Sorry, I had that student here working this morning that wasn't supposed to be here, so let me check if there was anything else that I wanted us to cover. But guys, the fact that you're so far ahead, I don't want to get too far ahead with you guys because I have to make that time up. Yeah, I closed that window. So if you guys want, you can go ahead and get out your computer for the last 10 minutes. That's all we have is 10 minutes left in here. I think all of that gets you up to quiz 2, which it didn't look like anyone had submitted yet, which is totally fine, but I think that's why I stopped, is that got us to quiz 2.